the data from in this case. And that's also why it's more urban, because I think COERC sets up the fiber network in Auckland urban areas. So that's part of our coverage limitation.
All right, I think we'll have to just wrap it up there. Sorry, you could ask Evelyn later. So join me in thanking Evelyn. Well, our next speaker and last speaker for the day is David Frost from McGill University, talking about metal fuels for zero carbon heat and power.
So thanks a lot for hanging around to the last talk. So I appreciate everybody being here. Really enjoyed the conference, seeing the context in New Zealand of these energy transition issues. I'm going to talk about something that's going to be a little bit under the radar. It's our work on metal fuels as a carbon-free energy source. And this is done in collaboration with my colleague, Jeff Berg-Thorson, and he runs the alternative fuels laboratory at McGill University. We're in Montreal, right downtown Montreal. I'm happy to be here in slightly warmer, not looking forward to going back. So maybe I'll just start talking. I think it goes without saying that we have to, move away from fossil fuels. And the question is, the difficulty of doing that is that the fossil fuels are so convenient and they're extremely, let me go to the first one, extremely high energy density. So in terms of the volumetric, looks like, oh yeah. Volumetric energy density is very high, as well as the specific energy. Excellent fuels are very easy to transport, but of course they have all of the downside issues, the supply issues, and also the pollutant and climate change issues. Now, I don't think there's any silver bullet to replace fossil fuels, but I think there is some silver buckshot, if you like. And we've seen some of this buckshot in this conference. There was some talk, one talk discussing, catalytically recycling carbon from the atmosphere. That was interesting, using biomass and so on. And so what we really need is an energy carrier. We want to take the energy from where it's being supplied from a renewable source and then bring it to where we need it. And ideally, we like to ship this worldwide. So that's really the difficulty. That's what we really need. And we need this energy carrier to be recyclable and also zero carbon. And so that's really the challenge. And we don't want any carbon emissions in the point of use or in the recycling stage. So there we go. Okay, so just before I get to talking about metals, I think there's been a paradigm shift in the last decade or so. 10 years ago, we think about fuels as something to burn to generate electricity. And if you look at the cost of fossil fuels, it's stayed relatively stable over that last decade or so. But in the meantime, the utility scale solar cost has dropped dramatically. So now we're at a point where there's actually a gap. There's a gap in this fuel to electricity price gap, allowing us to go so-called power to X. We can use this power now to do all sorts of different things, generating different types of fuels. And so this shifting from fuels to electricity to using electricity to producing fuels, I think is significant. Batteries and hydrogen, we've talked about them quite a bit. I think they're not enough to solve the problems. There's some issues. Really, the main issue for these two energy carriers, these are our energy carriers we have now, primarily. The main problem is a very low volumetric energy density. So you have to have, if you want to carry your hydrogen with you, you need a big fuel tank. Low mass energy density, also hydrogen tends to explode, and we know that because we've studied hydrogen explosions for about 4 decades in our research group. So, what's the alternative here? Well, let's step back and let's consider all possibilities. Okay, here's the periodic table. Which of these elements could be potential energy carriers? So I'm going to, first of all, eliminate ones that don't react, because we're going to have a reaction to get the energy out. So let's get rid of our non-reactive components in air and water. Let's get rid of things that are too heavy to carry around for us. What about ones that are too rare, too expensive? Let's not use those. I'd rather not use things that are toxic. You know, it's bad for customer relations, you know, you're poisoning people. So let's get rid of the toxic components. Things that react too slowly, well, you have to wait around forever. Very low power energy density. Too fast is also not good. And carbon, of course, that's what we're trying to avoid in the first place. So let's get rid of carbon. Let's take out hydrogen. And what are we left with? Well, we have these 7 elements, right? So let's take a look at these 7 elements and let's figure out how much of that metal would we actually need to burn to supply all of the world's energy needs. What is it? 15 terawatts or so continuously. So how much metal would you actually need to dig up and use? Well, this is the number here. This depends on the energy density. Iron and zinc are not terribly energetic. So you need this amount here. This is gigatons. And you'd need less boron, less aluminum. Boron is very energetic, but it's kind of hard to react. That's only 1/2 of the story. That's how much you would need, but how much is there in the ground? Okay, so what are the reserves? So this next one shows you the global resources available in the ground. And so from the comparison, what you need and what is available, potentially a couple of them jump out at you. Iron looks very interesting. Aluminum, silicon's a little harder to react. The other ones, there's really not enough around to be a serious player. So we really focused our research on these 2, iron and aluminum. Okay, so this is the basic cartoon, the schematic, energy carrier. What we want to do is we want to use renewable clean energy to reduce taking the oxide, metal oxide, which you dig up the ground, reduce that back to the metal, and then you ship the metal wherever you want around the world, and then burn it, and then use that to oxidize it, using that as a clean energy source. And so basically we're using metal fuel, metal oxide, as our circular loop. And so this really meets all of our needs for a renewable energy commodity, which can be easily shipped. You need an efficient recycling infrastructure. So this is, and it should ideally be without any greenhouse gas emissions. So this is iron oxide reduction to iron has now been decarbonized. Aluminum smelting is a little bit more difficult, but there is very interesting recent work. Rio Tinto, Alcoa have developed their ELYSIS system where they smelt aluminum with no carbon emissions. Apple's a big investor in that, and I think they're already using, in 2021, they demonstrated the technology, and they've used some of the aluminum to make iPads and iPhones already. And they're promising in 2024 to roll this out large scale. So we'll see, but that looks promising to, aluminum has been kind of a difficult, because of the energy consumption and also the greenhouse emissions. The metal you can store indefinitely, effectively reacts fast. So if you need high energy density, it's very attractive. It's also safe, non-toxic, and you can ship it worldwide. Okay, so let's put the metals onto the same plot. Energy density, aluminum, silicon, iron are 2 times or near 2 times the volumetric energy density of petrol, diesel. And this, you can actually burn metal powder in air. So these are pictures from our lab. This is just a Bunsen flame. And this is iron powder burning as effectively as a Bunsen flame. Burns about 2,000 degrees. This is aluminum burning at about over 3,000. And it's, in fact, so bright that you need goggles to look at it because it'll blind you. So extremely energetic. So this is burning with air. This is one way to do it. You can also burn it with water or react it with water. And you may be aware that aluminum water is actually a very good propellant. So here's actually some propellant strand tests we've done. Mixing aluminum water, ignite it, and it basically reacts, releasing hydrogen, leaving aluminum oxide. And at Purdue and Penn State, they actually stuck it into a rocket and showed this is actually good propellant. So you don't need a chemical propellant. You can use aluminum water. They took the aluminum mixed with water, froze it, and they call it aluminum ice or Alice, kind of like a popsicle, if you like, ice lolly, I guess you. So that's the two different ways to get the energy out. So this is kind of the cartoon of how it would work. You have the metal powder. Never find the metal powder here. You're putting it into a system where you're burning it and getting either generating electricity or transportation systems, power for that. You take the oxides and then recycle it back. You ship it to where you have clean renewable energy, and then you recycle the oxide back to the metal. So it's a circular loop, if you like. And how do you do this? Well, just to very quickly showing you the two ways. A dry cycle, burning with air. This is how you do it. You take the metal, you mix it in with air, put it into a reactor, and ideally you put it in a cyclone, because as it reacts, for example, iron powder produces iron oxide or rust. That gets thrown out to the outside and you just collect it at the bottom. You generate then hot nitrogen coming out, which then can be put into an external combustion engine. You can run a boiler if you like. So that's the dry cycle. And we've demonstrated all aspects of that. We take iron powder, put it in a feeder, add air. We have a turbulent iron flame. Show you in a picture what it looks like. This is the cyclone. Hot, clean exhaust comes out, no carbon. Oxidized iron fuel comes out. We ship it back to Tata Steel, and they recycled it for us and gave us the iron, and then we burned it again. So we've demonstrated the complete cycle. And there's the burner in operation, just a regular video, not slowed down or anything. So that's the dry cycle. The wet cycle is very interesting. That's where you take the metal, add to water, react it, and here's the cartoon again. Mix water, aluminum into the reactor. You get the metal oxide collection. And what comes out is you get hydrogen, hot hydrogen and steam, which then you could either put into a retrofitted diesel engine or into, say, a gas turbine engine. We're working with Siemens, who do the stationary gas turbines for power generation in Montreal. They're very interested in using this for generating hydrogen for their gas turbines. There's one trick to doing this. And first of all, I'll tell you that aluminum is incredibly energetic, because you take 1 liter of aluminum, you react with water, you produce equivalent to 4 liters of liquid hydrogen, plus the heat equivalent to 1 liter of diesel. So basically half the energy comes out as hydrogen, half the energy comes out thermally as heat. So you really want to use both of those. And the trick really is that we heard about aluminum, I think in the poster session, that it gets coated with this oxide immediately. And so you really want to have to add something to it to react, an catalyst. But it turns out if you mix aluminum and water and heat it up to supercritical conditions, the oxide dissolves and it reacts like crazy. So what we did was we took chunks of aluminum and put it into our reactor, heated it up, and this is temperature versus hydrogen yield. And you get to 373, the critical temperature. The oxide dissolves and the reaction goes to completion. So these big chunks of aluminum become aluminum oxide dust. And in fact, you don't need clean, like in the past, when people use aluminum water for propellants, they've basically had to use very fine aluminum, nanoscale aluminum, very expensive. Here you can just take scrap aluminum, take a aluminum can, and we just took this Coke can and chopped it up, stuck it in the reactor, and that was the product. 100% conversion to aluminum oxide. So that's my 1 minute. So this is my takeaway messages. If you have played with a children's sparkler, you know about metal combustion. That's, what is it? Potassium perchlorate and titanium, aluminum particles. They come out and they react. That's one of our stabilized flames. So basically it's a very convenient clean energy source that can be used in a circular manner, react with air, react with water. There's lots of challenges. We've looked at some of the techno-economic challenges. I can talk briefly, but it's already been implemented in some systems. For example, in the Netherlands, they have a iron powder system actually powering a boiler in the Swinkels beer brewery. So if you go to Netherlands, you can have iron power driven beer. Okay, so I think I'll stop there. Thank you very much.
Thank you, David. That was absolutely fascinating. Any questions from the floor?
Thank you very much. It's a really good presentation. Just a brief question, really. When we are kind of charging it, I do understand it's endothermic and exothermic reactions in its nature. When we are cycling the iron oxides, can we do that process to recover heat from, say, nuclear energy plants or some high heat waste plants, or does it need to be dedicated in certain facilities?
Yeah, you really want to do the recycling stage in wherever you have the cleanest and cheapest electricity. And so when we looked at that, if you want to do the complete life cycle analysis of the aluminum cycle, basically, if you want to compete with oil, we did an estimate. If the oil prices say between $50 and $100, I think it's like 80 at the moment, then you need electricity costs that are between 3 and 4 cents per kilowatt hour. If you have that, which we do in Quebec, then it's competitive with diesel as an energy source, and it's better than hydrogen, better than ammonia. So really you need cheap, clean electricity to do that, electricity intensive recycling. So it doesn't have to be, can be wherever you can ship it worldwide if you want to.
David, thank you. Great presentation. In terms of scalability, you started with fuels and gasoline and maybe diesel. Is there any chance to have it on a truck or vehicle fit size? Or is that one of the research questions you are heading?
Yeah, we actually have 3 startup companies from our students looking at the dry cycle, the wet cycle. And I think some of the targets are the maritime industry, particularly because you can use seawater, works well with seawater, so you don't have to carry your water with you. I don't think it's terribly useful for really small engines. So I think you need some economy of scale. So could be trucks. I mean, you can imagine having a capsule of aluminum water, which you basically plug into your device, you initiate the reaction and it produces hydrogen, either going into your diesel engine or into your fuel cell. And so basically, once it's reacted, gives you the hydrogen, you just pop it out, send it off for recycling, and then pop another one in. So, so there are interesting applications. I think the gas turbine engine industry is very interested, but it'll be larger scale systems or remote power generation where now you're using barrels and barrels of diesel and you want to replace that. So we have no other source of energy, then you can ship them the metal, burn it, produce electricity. So that's kind of the niche markets, remote, even mining operations.
Fascinating. I think we've run out of time, so we'll have to stop it there. But can you join me in thanking David and all our speakers?
Okay, so well done for making it to the end of the symposium, but we have one last event we'd like to do before we kind of close off, and that's to award the student prizes. So Greg, if you would like to come up. So these prizes were very generously provided by Energy Link, and so we'll have Greg present the prize. Students. Okay, so we'll start with the best poster presentation, And this goes to Varina Singh. Are you here? So, yeah. So the judges looked at all the posters, and you had done a very good job of explaining what you're doing, and a very sophisticated analysis. So thank you very much. So, could someone take some photos? Cell phone? Yeah, just. Thanks. And there's a prison card that goes with that. Sorry. Oh. Shake hands. Thanks a lot. Okay, and unfortunately, this student has already left. So this goes to Louis Medrano. So he presented in the first day. He did a presentation on a socio-technical post-occupancy evaluation to uncover elements of practice for reducing fuel poverty and performance gaps. So he had a very clear presentation and had obviously done a lot of work for his so we'll get this to him. So thank you very much for those prizes. So yeah, that brings us to the end. I hope you enjoyed the conference, and I guess any of you who, this is the first time you've come to an OERC event, please leave us your contact details, and we'll add you to our mailing list so that we can tell you of events in the future. And I guess we'll see the rest of you next year. So thanks very much.